Good afternoon, everybody. So today we will continue to talk about work. As we mentioned previously in our last class, we calculate work so that we can put it into the energy conservation equation, and work is either the energy input or an energy output to a system, right? So before we start, just want to check in. Anybody can still recall what is the definition for work? How do we calculate work? Work is defined as, how do we calculate work? Okay. Work is force times displacement. No, thank you, Eric. Work is distance times force. Yes, so if we are, in general terms, we say force times distance, right? You apply a force for a certain amount of distance, and that's work. But if we want to be more accurate in our definition, remember, we keep on improving our definition. Well, that distance, sometimes it depends on the route that you're taking. Sometimes it only matters what your beginning and your end point is. So for some of the forces, as we will see today, you do need to use the distance. And some of the forces, you have to look at the displacement. And also the force could change, right? So the force could be different at different locations. So to be more accurate in our definition, work is defined as the integral of force dot into the displacement dr. But if your force is a constant, then that's simply F dot into delta R, force dot into displacement, okay? So we will try to use this idea to look at all the work that can be done by different forces. So gravity or kinetic friction, or what about static friction, spring, and normal force. So this is what we're going to do today. And we're going to plug that into energy equation to solve more energy conservation of energy problems. Start by work done by gravity. Okay, so we have this scenario. We have a block M that's at first is at the height h above ground, and then go to the bottom of the ramp. So there are two different kind of ramp. One is at a smaller angle, one is at a bigger angle, but they're all the same height from the ground. So let's calculate the work done by gravity in the two situations. Do you think the work done here is the same or not? Okay, so you may have a prediction in your mind. So let's calculate the work together and see if they are the same. We're gonna do the first one. Okay, so we calculate work, right? Recall this definition, and we need force dot into displacement. Let's look at the work done by gravity here. The force is force of gravity pointing down. Okay, so that's Fg, right? And displacement, you go from here to here, so you're going downward, right? So I'm going to draw my displacement arrow that is going down parallel to my incline, right? Parallel to the surface. So that's delta R. And they have an angle between them. Notice that the angle is given. So the perpendicular and along the incline is the phi, right? So it's this angle, which is given. That's as is drawing on the incline. So let's do the work done in this case 1 or 2. Case 1, the work done by gravity is the force dot into displacement. And how do we calculate dot product? Do you still remember? We do the force magnitude times displacement. The magnitude times, is it cosine of the angle between them, or is it the sine of angle between them for the dot product?
It's cosine.
It's the cosine, yes, very good. It's the cosine of the angle between them, and the angle as indicated C in the picture. So let's look at what would this give us. So this is going to be mg, and this is going to be the length of the ramp, right? The ramp has a entire length, let's say call it L. So L cosine of phi. So if we look at this triangle of the ramp, the L is a hypotenuse. So L times cosine phi, what does that give us in the picture? This is L. This is phi. L times cosine phi give us which one? Which height? give us the adjacent of the triangle, right? Which is h. So L cosine phi is the height, h. So you got mgh. That might look very familiar, right? As in gravitational potential energy is also mgh. And it's no coincidence that they're the same. I'll talk about why that is in a minute. So if we are to calculate the work done by a tool, do you think I need to redo this calculation? Or do you think I would know what the work done in case 2 right away without doing the calculation? What is the work done by gravity in situation 2 at a different ramp? So I will still do force of gravity, displacement, and the angle between them. As you can see that if I use that displacement, the total length of the ramp, times the angle cosine phi, I will still get mgh. Thank you, Kenneth. That is indeed correct. We get same thing. So you can see that the work done by gravity is independent of the path that you're taking. And it only depend on what your start point and your final point. You only depend on what is the vertical distance between those 2 points. Even if you take a curved path or bumpy path, the shortest distance or a longer distance doesn't matter. The work done by gravity only depend on the beginning and the end point. And you can see that this is a point of view that you will take if you view gravitational force as the external force. So work, the gravitational force to work on the block. But if you view gravity to be part of your system, if you view Earth as part of your system, you will not talk about work done by gravity. You will talk about the gravitational potential energy instead. So no matter where you put it in your energy equation, you will have the mgh term. So this is no coincidence that the work done by gravity has the same format as gravitational potential energy. It's really just a perspective of how you want to view your system. We will later on have a concrete example to show what I mean by different choice of system. But anyway, we have calculated work done by gravity, and is mgh. From now on, you know it's mgh is work done by gravity is only depend on the height. If you're going down, gravity does positive work, right? Because the force and the displacement in the same direction. If you're going up, gravity does negative work. And this work is independent of the path taken. And we call these type of forces, we give it a name, we call them conservative forces. Don't stress too much about the name. It's really just, okay, we give this force a category, a name. Now there are non-conservative forces, which means you do have to think about the path. The example for that is the frictional force, right? If you have, think about the friction, right? If you take a longer path, wiggle around, you can see that you're generating more heat, right? That is corresponding to more energy transfer. So definitely the path will make a difference in terms of the frictional force. We will look at that difference between these two work by these two different forces using a concrete example here. So we have a first question. You push a 1 kilogram mass and moving on the wall around a square loop. It's 1 meters per side. And you start here and you go around, you finish here. So I'm asking, what is the work done by the gravitational force during this journey? I'm gonna go ahead and let you vote. You may need to take a moment. If you need to quickly calculate on your scratch paper, you can do so, but we don't need to go discuss this question. So just use what we talked about. How do you calculate work done by gravity? Okay, 10 more seconds. 10 more seconds. Please put in your vote. All right, I'm going to go ahead and close this, okay? Let's look at our results. It looks like we are all agree on the magnitude. At least we know how to calculate the amount of the total work done if we want to know the absolute value of that work. But the disagreement is between B and D is the sign of it, whether it's a positive or negative work. So can anybody share with us, what do you think? From this starting point to this finish point as shown, indicated here, do you think work done by gravity is positive or negative?
Positive.
And how do we know? How can we tell? The direction of the gravity is pointing which way? Is pointing downward. Very good. And someone said because the direction of the gravity is the same direction as your displacement. Very good. Your displacement from beginning to the end is going down, right? This displacement is going down. That is 0.5 meters, and that's downward. Gravity is also down. So you put it together, you got a positive work done. Very good. You put in your mg and the height, you got 5 joules. Excellent. So you could, you have two ways to do this. One is figure out the magnitude and you figure out what the sign of this is. Or you can do force of gravity dot into displacement and you will say mg times 0.5 and the angle between them, right? You're using angle to take care of the sign here. In this case, they're in the same direction. You have a cosine of 0 degrees and that is 1. Okay, so if the opposite signs at 180 degrees, you get -1. You can either look at the signs and you just put the sign in there, or you can do the calculation of the dot product. So either way, it's fine. Now let's look at the work done by friction of this journey. Okay, and I tell you what the friction is. There are 2 newtons. And you know that friction, the work is again, is this times displacement, okay? So here the frictional force is 2 newtons. Think about what is the work done by friction during this journey. Okay. I'll give you 2 minutes in breakout rooms, okay, for this question. Let's go for 10 more seconds. All right, I'm gonna go ahead and close this. So this is our results. So there's some votes for the positive ones, and we can kind of remember this trick. I would claim that the work done by friction, kinetic friction, is always negative. And why isn't always negative? Let's think about the way that kinetic friction is pointing. Kinetic friction is always opposing the direction that you're moving, right? So the direction the kinetic friction is always going to be opposite direction to your displacement. It's always in the opposite direction where you're moving. So for that reason, we know the work done by friction, the kinetic friction is always negative. So we kind of have narrowed it down to the two answer choices here. And in terms of calculating it, can we simply use the magnitude of 2 newtons times the displacement of a half a meter and add a negative sign? You notice that it's not even an option here, right? You don't have 1 joules, right? The kinetic friction depends on the path you're taking, right? So this -7 is correct because you have to think about all the distance you travel through. Kinetic friction is in the opposite, different direction for all these different paths, 1, 2, and 3, and 4. So in this here, you're going up, your kinetic friction is going down. But in the route 2, you're going to the left, so friction is going to the right, right? The direction of friction always changes directions, indicating you need to separate these calculations into the 4 different stages. And as a matter of fact, since they're always opposing each other, is equivalent of looking in the friction times the total distance you're looking at. So it's going to be 2 newtons times 3.5 meters, and it's always negative. So that's -7 joules, as D is saying, okay? So you can see the difference between work done by gravity and work done by kinetic friction. So now let's look at work done by static friction. This is a quote from a student, and think about whether it's correct. This student says, I don't think static friction can do work, because if it is static, then that means there's no motion, isn't it? The motion, the object is at rest, so there will be no displacement. Then work is 0 because F dot into displacement is 0. Think about whether you agree or disagree with the student. He or she is correct in the sense that it's static means there's no relative motion between the object and the surface of the object is at, but doesn't mean the object is at rest. So I'm going to show you an example, which is a checkpoint question you have already done. In this case, you have a truck that is accelerating to the left, and you can see you have this box sitting on the bed inside the truck, right? It is accelerating together with the truck. And how so? Because there must be a force that's providing this acceleration. Where does this force come from? It must come from static friction, right? So can anybody tell me in which direction do you think the static friction is acting on the box? Is the static friction to the left or to the right?
Left.
To the left. Then it has to be to the left to provide that acceleration, so the box is moving together with the truck to the left. So they are at rest to each other, but they're not at rest viewing from someone standing on the ground. So you can see that this box certainly is moving with some distance, right? As you go to the right, some displacement, and friction is pointing to the right, to the left as well. So the work done by static friction is positive in this case. So static friction can do work. So that's a counterexample of what the statement by the student, which was given. So so far we have done work done by gravity, kinetic friction, and static friction. Now let's look at work done by a spring force. This is a little bit harder to do, as we do have to do the integral now, because the spring force is a variable that changes with how much your spring is being compressed, right? So for example, let's look at this calculates using area under the curve method. So the force is negative kx, that's given by Hooke's law. You still remember Hooke's law, right? So you have the force is always in the opposite direction of your displacement. So you have a line that's kind of below the x-axis. So from x1 to x2, to look at this area under the curve, we can do the integral of negative kx dx from x1 to x2, right? And you have 1/2 kx squared using our math about integration, x1 to x2, and then you can calculate how much work is being done, right? It's x2 squared minus x1 squared. Okay. And you can see that the work done by spring, this format 1/2 kx squared, as was showing in here, is very similar to a type of potential energy, right? Do you still recall? That is the potential energy of the spring, right? Which is 1/2 k delta x squared. And this is just like how gravitational force, the work done by gravitational force is the same format as your gravitational potential energy, right, mgh. So you can view this by either include your spring in your system or not. If you include spring in your system, you will talk about this change using the change in potential energy that's stored in your spring. But if you don't include spring in your system, you will look at this as if spring has done work onto your block, and it's no coincidence that they have the same format. Okay, so that's how you calculate work done by a spring. The last question I want to mention this because it summarizes all the different forces before we move on to talk about energy transfers. So let's look at 3 different scenarios. Scenario 1 is a free fall. Scenario 2, an object going down an incline that has no friction. Scenario number 3, you have a sort of a pendulum. So it's asking which case does the object have the biggest net work done on it by all forces during its motion? So let's look at them one by one. The first one, the only force acting on the object during free fall is the gravitational force, right? So here, all the work done is simply the work done by gravity, which is mg times height h, positive. Second case, there are how many forces on the object? We have gravity. Do we have another force? I know I don't have friction because it says frictionless. Do I have another force?
No.
Normal force?
Yes, one more, that's normal force provided by the surface of an incline. Only those 2 forces, right? And the work done by network. So all the work done by individual forces added together. First, you have the work done by gravity, and you think if there's a work done by normal force adding together. The work done by gravity, again, is mg, and again, only depending on the beginning and the ending point, regardless of the path you're taking. So we're going to say mgh. The work done by normal force. What is the work done by normal force? Displacement. Is it 0? Yeah, it is 0. Why is it 0?
There's no movement in the opposite direction of gravity, or it's going down one path.
Yeah, the path is taking, the displacement is perpendicular to your normal force. Okay, my screen is frozen. I have to go ahead and share it again. So just give me 1 second. So it's 0. The third case, well, I have gravity always. And since I have a rope here, I have tension. My tension is aligned inside in the same direction as my rope. So here, work done by gravity plus the work done by tension. Work done by gravity, again, is mgh, right, from here to here. So do you think there's any work done by this tension force?
No.
No, because it's always, the tension is along the rope. Only if you have a displacement along the rope, then you'll have a work. But you can see no matter where you are, your displacement is always tangential to the path, you can see it's always perpendicular to your rope, and that's 0. So so for this problem, it will say all the same because the normal force and the tension in this case doesn't do work. The only one that is left is gravity. Okay, so before we do the energy transfer, there is one extra concept to mention that's called the power. And we use power in our daily lives. Is defined to be the rate at which work is done, right? So use an example of you can walk upstairs or you can run upstairs. As in terms of how much work is being done by gravity, it's the same work, the same amount of work. But the one that takes less time has much bigger power. Same thing with your electrical appliances at home, right? 1,000 watts versus 5 watts. You use electricity for same amount of time, you will use different kind of energies because the power is different. So it's at what rate the work is done. So the power can be calculated using change of work, the amount of work divided by time. Of course, this is the average power. The instantaneous power is a derivative of work over time, dW over dt. The units are watts. I'm sure you're familiar with that, right? We have talked about watts when we talk about our light bulbs and microwaves. The more watts it is, meaning that at the same amount of time, it's going to use more energy. Of course, that there are other units. Sometimes people use horsepower. Then you simply just need to do a unit conversion to get it to watts, which is the joules per second. Okay, so we finally have the tools that we need to do all the kind of problems we need to do for energy conservation, because we know how to calculate energy input and output when we know this can be calculated using work. One thing to be noticing is when you plug in work into inputs and outputs, we always plug in the absolute values. Because just like when you said, I take money out of my account, $500, it is an output, right? But the negative sign is already taken care of by putting in here. So when you put the number into your output or input, you always put in an absolute value. So even if you have work done that's negative work, for example, work done by friction is 100 joules. That's work it taking out of your system, right? So you're putting 100 joules in here instead of negative 100. So work done by friction will be negative, but when you plug it into energy output, you use 100 as a positive number, okay? So we'll see them in concrete examples as below. So for example, here is one of the problem. We have a hockey puck sliding with 4 meters per second, slides without friction along a frozen lake on a ramp and kind of go up a hill of 1 meters high. We assume just use 10 to be a little bit more convenient. So the question is, will the puck make it all the way up the ramp? Is 4 meters per second, how high is it going to go? Is it going to go up to 1 meters? So this is a problem we're trying to solve using conservation of energy. So before you go ahead and do that, again, I want to model the steps of solving these type of problems. As we said earlier, for any kind of physics problem, first you draw a picture to visualize the situation. You label the quantities, mass, velocity, and whatsoever, put it on your picture, and you decide what is the question. Okay, so this question, will the puck make it all the way to the ramp? Now realize that didn't really tell you what quantity to solve for. You have to figure out which quantity you want to solve for. Okay, decide on what question you want to answer. And then these steps are specific for conservation of energy problems. First of all, choose a system. What system you're talking about? Is it the ramp only? Is it puck only? Or is it puck plus earth? Or sometimes you want to include the spring. And then define an initial and the final moment. And then 3, you find final energy, initial energy, energy input and output, different type of energies. And last, you plug these different energies into your energy conservation equation and solve for the unknown. So these are the steps we will be taking. Okay. So think about this problem. I'll give you some time and to discuss it in groups. And for example, we can use different systems. System 1, you can use puck only, or system 2, we can use puck and earth. So I believe system 2, most of the time, it's always easier to include earth in the system. So let's answer that question first. Sorry, puck and earth is here. So think about all these different terms. I have already given you limited choices. What do you think these terms would be if you're talking about puck and earth system? And of course, I have already defined initial and final moment for you. So I have defined initial moment is here at the bottom. Final moment being the puck is all the way up the ramp. Okay. So think about which of these choices is correct. And after that, we can use that to solve our problems. So take some moment to discuss within your groups.
Professor?
Okay, so any last minute vote for this question? All right, let's take a look at this together. This is our results for the system of choice of puck plus earth system. So I have defined the initial moment to be when the puck is at the bottom of the ramp, and final to be when the puck is going at the highest point possible. So not necessarily at 1 meters, because that's what we're trying to figure out, whether it can go up that high. So the final moment is it go up as high as it could go, and as up at point h above the ground. So what are all the energies? Energy initial would be the energy the system puck plus earth had at the bottom of the ramp. So at this point, what kind of energy do you think we have?
Kinetic.
We have kinetic energy. Very good. That is because the puck is moving, and we can define this as a reference point, so you don't have to think about the potential energy. You're at this ground zero, zero above the ground. And final, when the puck is the highest point, what kind of energy are we going to talk about? Seen from the answer choices, we agree we want to talk about potential energy, right? Yes. So it's going to be potential energy of the puck plus earth system is going to be mgh at a height h above ground. At this point, the puck is not moving because it has gone as high as possible, so you don't do kinetic energy. There is no energy input, as you can see that there's no force that's constantly pushing the puck up or making it go faster, so there's no energy input. And if there's no friction, there's no energy output. Here we're talking about a puck going up an ice ramp, so which indicate there is no friction, right? So there's no energy output. The work done by kinetic friction will always be energy output. So these two are all zero. So looking at the responses, C is indeed the correct answer. Okay. So we'll talk about the other choices later, but let's first solve this problem. So let's plug everything in. Final mgh, initial 1/2 mv squared equals input and output. So we have solved for which quantity? We have solved for, which quantity are we trying to solve for? Now it comes to the question. What is the question? We want to know if the puck could make all the way to the ramp that was originally set at 1 meter, right? So we instead are going to solve for, we're going to solve for the highest point it can go, which is h. It may not be 1 meter, it might be 1/2 meter, or it might be 1.5 meters. So it can even go up higher than the ramp we were given. That's all okay. But we want to know what is this height h. So the question is, what is h? So we know from this equation, we need to solve for h, which will be v squared over 2g. That's your answer, right? You can plug in the numbers with v is 4 meters per second, with this as 10. So that's 16 meters second squared over 20 second squared. And that's slightly less than 1 meter, right? So this is less than 1 meter, and you know that it's not going to make it up the ramp, okay? Because height h is smaller than the ramp that was given. Okay, so we have done this. You can see a very quick calculation using this particular puck and earth system. Now, you can see that this one, the difference between choice A and C is choice A has work done by gravity. I would argue work done by gravity in this case is not an energy output because you have included earth in your system. So it's part of you now. It's an internal force that doesn't do work on your system. It's your left hand punch your right hand, right? That doesn't change the status of the motion. So if you were wish to use puck as the system, that is also okay. So now let's exclude earth from our system. We choose puck instead. Can we find these 4 different energy terms, and are they going to be any different from before? So I want to let you guys go ahead and vote here. I don't think we need to discuss, but just go ahead and vote. What do you think the answer would be different if we change the system to be just the puck without the earth? Okay, so 10 more seconds. If you haven't voted already, please do so. All right, any last minute vote? All right, let's take a look at this together. So if we choose PUC as a system, how would you revise your different terms? Seems like we have a majority answer for A. Okay, and relatively equal between B and C. So if we don't include Earth in our system, can we talk about the gravitational potential energy? We have emphasized that if you want to have gravitational potential energy, you have to include Earth in your system. So if you only use PUC, you cannot talk about the potential energy, okay? You do need to think about gravity, right? So if we were to choose AC, how is this going to work out in our energy equation? So you will plug these each individual into this energy equation. Now, final energy, if it's potential energy, you would do mgh. Initial is kinetic energy. Input is 0, output is work done by gravity, so you will have that mgh again. So you have these show up 2 times. What do we end up with? You will end up with you either will have work done by gravity or you will have potential energy. You cannot have both of them in the term, right? So this one indicates you have included Earth in your system. This one indicates you have excluded Earth in your system. You have to pick one and stick with it. So in this case, the final energy should be 0 because the PUC has stopped. As far as the PUC system, that's all the energy. So energy final should be 0. And in terms of initial, it's still the kinetic, no inputs, the output is indeed worked on by gravity. You're right, because now gravity is doing negative work on the PUC, it's slowing the PUC down, right? So you can think of all the kinetic energy of the PUC now is being transferred out, and the work done is through the work done by gravity. So B is correct. And let's use this PUC system to solve our problem to see if the answer is the same. So I'm going to use the same location. In one thing that's changed is our system. Your E initial is the same, 1/2 mv squared. E final is 0. E in is 0. E out is worked on by gravity. Okay, work done by gravity is negative, but in terms of energy transfers, we want to do the absolute value, so it's mgh. So let's put everything together to see if we get the same result. The final is 0, initial is 1/2 mv squared, input is 0, and the output is mgh. Okay, so you get the same result, right? 1/2 mv squared equals mgh, and h is v squared over 2g, just like what we got here, right? So these 2 different methods is a different choice of your system. The system is totally up to you whether you want to include the Earth or not. So you have flexibility in choosing which system you want to evaluate, and then you put on the energy terms. Okay, so that is just one quick example to showing how you use energy transfers into your calculation. Now let's include the spring. The second example has a spring in it. So at the train station, you notice a large horizontal spring at the end of the track where the train comes in. So you have a train that is coming in. Here you have a spring in here. This is a safety device to stop the train so that it will not plow through the station if the engineer misjudged the stopping distance. While waiting, you wonder what would be the fastest train the spring could stop at its full compression, which is 3 feet. The max amount of the distance the spring can be compressed is 3 feet. To keep the passenger safe, when the train stops, you assume that the maximum stopping acceleration of the train caused by the spring is g/2. Okay, so it's telling you the maximum stopping acceleration. So that gives you some information about the spring constant, right? So here you can know, you figure out something about the spring constant. You make a guess that the train must have a mass of 0.5 kilograms. For the purpose of getting an estimate, assume all friction is negligible. So you don't think of friction. So this question is what we call a real world problem that is worded in a real, like a real world situation. You don't necessarily tell you what quantity to solve for. You have to decide what is the quantity you have to solve for. So by reading this statement, I think this is where we trying to figure out the question we're trying to solve for. You wonder what would be the fastest train that the spring could stop. So it seems like what would be the fastest? You're looking for its speed. That is the quantity we're trying to solve for. Okay, so you must, so to be safe, this is the speed the train can come in with, so that when the spring is fully compressed, then the train must also stop at the moment to be safe, right? So they tell you something about the final velocity of the train. So there's a lot of information in there that we have to sort of extract ourselves. All right, so given this problem, you can take a screenshot to save it if you need, but I'm going to present you the options of the next question. So I'll give you, I stop for 5 seconds if you need to take a screenshot. Okay. So let's try to use different systems. The first system, you can choose to include the spring in your system, and or you can exclude it. Here, I didn't talk about Earth. Now, why is that? Because the train is going in the horizontal direction. There is not going to be any change in your potential energy, or there is not going to be any work done by gravity. Therefore, I did not bother to talk about the Earth in the system. Okay, so if we use train and spring as our system, what are all these terms? Again, take a couple minutes to discuss within your group. You can take a screenshot before you go. So as people put in the vote, just want to talk about how we define our initial final moment. We choose train and spring in as our system. Initial moment is when your train first comes in with some speed. And the final moment is when your train stops. And we want to figure out what is the fastest speed that the train can come in, so that when your spring is being compressed to the maximum amount, the train also happens to be stopped at the moment. So you can either say your final moment to be when the spring is fully compressed, or your final moment is your train is fully stopped. That's the same moment. Okay. So with those two moments, we're trying to define these energy terms at each point, at initial and final point, as well as whether you have any inputs or outputs. All right, so we included the spring in your system. So how would that affect your choice of your energy terms? Okay, 10 more seconds. If you haven't voted already, please do so. All right, any last minute vote? All right, let's take a look at our results. This is our results. The majority voted for A, and there are quite a bit voted for B. So we say we don't have work done by gravity because the train is now moving in the horizontal direction, right? So you're not going up or down. All right. So a difference between A and B is whether in A you have potential energy of the spring, but in B you have work done by spring. So how do we figure that out? You included the spring in your system. So that means you do have to think about the potential energy of the spring, right? So let's work out these terms. Initial energy, what kind of energy do we have? Initially, when the train is moving, it's coming in, we have kinetic energy, right? So we have kinetic energy of this train is 1/2 mv squared. And we want to figure out what is this velocity we can have. And the final moment is when your spring is at its maximum compression, which means your train has stopped. No kinetic energy, but you do have potential energy. So the potential energy of this spring is 1/2 K delta X squared. Delta X is how much your spring is being compressed. There is no energy input. There is actually, if you don't think about friction, there's no energy output. So I would say A is correct. Now, your B would have been the correct answer if you are using train as your system, okay? So if you use train as your system, you don't have spring, so you cannot talk about energy stored in the spring. But instead, you can do work done by your spring because spring is now an external force, right? Spring is external, so it can do work. It's just like how we included and excluded Earth in the previous problem. Okay, so if we use this approach, we can solve the problem fairly quickly by putting all these terms in there. velocity is square root of k over m times delta x. And we realize we don't have k, but it has one information that's in there saying to keep the passenger safe, this stopping acceleration is g over 2. So that is another way to tell you what the spring constant is. At the maximum impression using Hooke's law, F equals ma, and a is given as g over 2. So that is telling you what the spring constant is going to be. So spring constant k is mg over 2 times delta x. So you can plug that in here to find what the final velocity, what is the initial velocity the spring can, the train can have in order for you to stop it at a maximum compression. Okay, so the overall final result is V naught is square root of g times delta x over 2. Okay, so that's your answer. You can use your train as your system, which I encourage to do here at home. So instead of doing energy of the spring, you will do work done by the spring. So the result should also be the same. We don't really have much time left. For the last problem, I just wanted to sort of set it up, and then you can look at my solution later on outside of a class. This one has to do with the work done by friction. So here, basically, I will just summarize the problem for you. You're sliding up some little puck up a ramp, and you want to land it within a certain zone to win a prize, and you have certain speed you are like sliding the puck with, and there is some kinetic friction to slow the puck down. So you want to find out how far you can go up the ramp in order to see if you win the prize. Problem we have the puck going up a ramp, and we do also have friction. We haven't done anything with friction before, so I want to use this as an example to show how do we solve that kind of problems. So you're going up the ramp is 37 degrees, and you go up for some certain amount of distance. Let's call it h, and you want to see how far you're going up the ramp at the distance d. Kinetic friction is coefficient is 0.8, and your weight of the ramp is 2.5 pounds. So we want to solve for what is d. So let's say I'm going to just set it up for you, and you can finish the rest of it at home. I always like to talk about potential energy. So when can I include Earth in my system? Now, if you don't like that, you can delete Earth, and then you have to think about work done by gravity. That's up to you. So energy initial, it's just the puck moving, right, at the bottom of the ramp. So I only have kinetic energy. Final energy, the puck stopped at a distance. So you have potential energy in the system instead. So it's mgh. So this is your initial. This is final. There is no energy input again. Someone might say, what about you swing? You swing, you give the speed and you let go right away. So after you let go, there's no other forces keep it from going faster and faster. So you don't have any energy input. The work done by friction will be serving as an energy output. So you will put it here, work done by friction. Okay, so work done by friction is F friction dot into displacement. Friction is opposite to your displacement, so it's negative frictional force times the total distance you travel. And again, how do you calculate frictional force? It's mu times normal force, right? So mu times n times distance. Again, what is your normal force? Here you have a normal force that is up on the ramp. Hopefully you still remember the normal force for something on the ramp is mg cosine theta. So you can see that it worked done by friction on the ramp. After all these steps is mu mg cosine theta times d. So you can plug everything back into the energy equation. And we want to solve for this distance d. Okay, so you can see work done by friction is negative, but when I put it into energy output, I'm looking at the absolute value of it. So final energy is mgh. The initial energy is 1/2 mv squared. Energy input is 0, output is this mu k mg cosine theta times d. So you can put everything together and solve for the distance it traveled, which will be this particular result. I know I worked through this very relatively quickly, but I encourage you to go home to look at, okay, can you solve this problem using different choice of your system? I just use Puck and Earth. Can you use Puck? Can you do this again with Puck? Would you get the same result? So I encourage you to do that when you get a chance at home, okay? So we tried 3 different problems today in class. One is really just a kinetic energy and potential energy, gravitational potential energy. The second one involves the spring energy, and third one involves both the work done by friction and also the kinetic and potential energy of the Earth. Okay, so 3 different type of problems that give you a good representation of the type of conservation of energy problems we will encounter in this chapter. All right, so I'll upload these notes and then go home and try to finish what we didn't do in class. For example, if we do one system and didn't use the other, I want you to solve the problem again using a different choice of system. And I would say the easiest way to solve problems is when you can include Earth, you always include Earth. And when you can include spring, always include spring. Because that way you will always just have mgh as your potential energy for the Earth, and you have 1/2 k delta x squared for the energy that's stored in the spring. Now, if you do work done by gravity, work done by spring, and that's a little bit harder, right? Because you have to think about, is this an energy input or output? And is it going to be positive or negative? So that's a little bit harder. All right. So, okay. So that's pretty much we have all for today. That is concluding our discussion on conservation of energy. And we will begin a new chapter starting on Thursday, which is the center of mass and the conservation of momentum. All right, so that's all for today. I'll see you guys on Thursday.
Bye, Professor. Have a good one.
Thank you, Professor. Have a good
Thank you. You guys
Thank you, Professor.
Thank you, Professor. Have
Thank
a great
you.
weekend. See you on Thursday.
see you on Thursday.
Actually, Professor.
Yeah.
Are you able to answer questions right now? Like quick questions?
A quick one, like a real quick one.
Yeah. So I was looking through my Flip It physics thing yesterday, and I saw one of the checkpoints was all red, even though I did the checkpoint question and all that. What am I supposed to do about that?
Okay, so why don't you take a screenshot of that and let me get back to you. I can probably fix it, or if not, I'll fix it in the grade book.
All right. Do you want me to just what do you want me to take a screenshot of? Like,
where you see that red showing up. And send
all
it.
right.
Okay. Send that email to me with that screenshot of the question you're looking at that shows up as red.
All right.
Okay. All right.
Thank you, Professor.
No problem.